All right, everyone. This video is going to be a replacement of me being in class. I'm sorry I won't be here in class with you on the last day before, I guess, the last day I was supposed to see you this year before the holidays. But yeah, due to some family issues, I am going to be away. I hope that this will suffice. Please don't give the substitute a hard time. And for the substitute, who is playing this video, would you please, in your own discretion, pause this video when you feel necessary for students to copy down. You may also notice as we move on that my writing might be a little atrocious because I have somehow lost my stylus and I'm writing everything using a mouse. So let's get to it. 7.2 is essentially a two-parter. You'll see more of it when we come back from the break, but it's essentially exponentials and by extension logarithms, how to solve equations that involve exponentials or logarithms. So the first part is going to be exponentials. Here are all these different examples that involve exponents. How do we get around them? How can we use logarithms for our benefit, to our advantage, to solve seemingly impossible questions and solve for x. And then the second part, you're going to see the exact same stuff, but learn techniques for logarithmic equations as well. So let's get to it. Solving equations is good, but why is it necessary? You've heard me say it before, lots of applications, of exponents in the natural world like Halflife, investment growth, sound, etc. And it is ideal to have the ability to make comparisons in mathematics. It would be silly if we couldn't do that, or if we weren't able to do that mathematically um, after, successfully completing grade 12 math. Some of the more simple things that we can do, we can compare graphically for sure. Visually, it's easy. Like for example, let's say I give you two exponential curves, find and count to and your goal would be to identify which curve is better. So curve A and B represents battery life for a novel electric vehicle. When is battery A better than B? So better is sort of subjective. Are you talking about better as in longer battery life? Are you talking about better as in providing more voltage? It depends. So let's, for the sake of clarity, let's pretend being better means having a higher Y value. That could be voltage, that could be just anything. So being a better battery, this question would be referring to all the parts of this curve where the A curve is higher than the B curve. So essentially right there. And that point right there would be my point of intersection, which in this particular case would be just at the whatever the parameters are, x versus y, uh, when the y value is equal to each other. Okay, so that's just visual, and it doesn't really help us mathematically. It just sort of gets you to understand what we're talking about here. Example 2, as opposed to giving you curves, I can give you two different exponential curves and ask you when is the value of x, at what value of x are these two equal? So every single one of these, understand that I'm trying to figure out what that might be. Maybe that might paint a better picture of why we're doing this. So let's get an equation like this. How do we solve this? There's a variety of ways you can do so, but for this particular example, I'm going to try to introduce this interesting technique where I log both sides. So again, let's pretend A equals B. If I plugged in A into a function and I plugged B into a function, since those two numbers are equal, when I plug it into a function, the y value should also be equal to. In the same way, if I decide to log and plug in 4 to the power of 2x minus 1 into this log, I should get the same answer as logging and putting 3x plus 2 as my input. Okay? And the reason I'm doing that is because the x value is an exponent. It's pretty difficult to actually solve while keeping the x as an exponent. So what I'm going to do is, if I were to log both sides, I would be able to use the power law to bring the exponent down as a coefficient. And when I do so, I have 2x minus 1 multiplied by log of 4. And then my coefficient would be x plus 2, leaving log of 3. And you know that log 4 you can plug into the calculator. Log 3 you can plug into the calculator. Essentially what you're going to do is what you're going to have is a decimal multiplying with the binomial, a decimal multiplying with the binomial. I can simplify this and say the previous line is equal to 0.602 multiplied by 2x minus 1 equals log 3 is 0.477 approximately multiplied by x plus 2. And the rest is simple algebra. You can do distributive property and then solve for x. And just know I'm not going to complete it. I'll let you finish it because I'm not going to insult your intelligence. You should know how to do so. X is going to equal approximately 2.140. See if you can get that. Right? At this time, the substitute could sort of pause the video as they see fit to see if anyone needs to copy, or also give them some time to finish this on their own and see if they're able to get it. The final, I guess, the summary or the conclusion for example 2 is, in times like this, all you really have to do is log both sides, and you are able to use a lot of your power laws or law of logs to simplify the question. Okay, I'll take a moment to pause and copy down. I will move on to example 3. Example 3 is a formula, so comparing before and after situations. That's a lot more sort of, I guess, word question based. In this particular example, it's Half-Life. So in this formula, it's the final amount is equal to the initial amount multiplied by half, so 0.5 or 50%, to the power of some exponential function that has the half-life parameter inside it. Okay, you'll see what this means in a second if you're still not familiar or if you haven't done too much sciences. This is really interesting, shameless plug, and it's going to be a quick story time. I hope you'll understand. I find this part to be really interesting because, I don't know, it's just a very, very, very good plug into the scientific world. If you didn't know, or if you don't have someone close to you or nearby you that has ever had an issue with their thyroid, that's a little organ on their neck. The thyroid is largely it's responsible for a lot of good hormones in your body. Things like growth hormone allowing you to, allowing you to get bigger and stronger. Also regulating sort of healing hormones, quote unquote, that when you're sleeping, it regulates a lot of good hormones in your body and allows you to repair damage that might be done, whether chemically or physically or whatnot, to your body. What's interesting is that particular organ, the thyroid, collects all the iodine in your body and sort of stores it in the thyroid. And it will release the iodine as it needs, as your body needs, which isn't a lot, but ever so often you need to replenish the storage in your thyroid. If you don't, you get this thing called a hyperthyroidism, which is basically your thyroid overcompensating, like feeling like it's not producing the hormones that your body needs and doing its best to overcompensate and getting thicker and stronger, like an overworked muscle, like Arnold Schwarzenegger in Muscle Builders, but still not producing enough of the good hormones because it's lacking iodine as a building block. So here's a story. A lot of people in the East Asian culture, as you know, I am Korean, have a large part of their diet, their staple diet, taken from the sea. So fish, seaweed, sea salt is a huge portion of our daily, I guess, diet. And sea salt has iodine already mixed in. It's a very nutritious kind of salt with high nutrients. But whereas Western meals don't necessarily have that. You put salt in your foods and to make your food taste better, but it's not really laced with iodine. And so when Asian people, for example, moved to the West and immigrated, they ate their normal foods and they seasoned their salt with regular salt. And guess what happened? A vast majority of these people started developing hyperthyroidism or problems with their thyroid to the point where it just overgrew. Some people just had goiters or some like overgrown neck lumps. It was terrible. And they were able to identify that iodine was the cause. And now every table salt product that you buy in the supermarkets, you will see that it has been iodine infused or iodine enhanced or iodine whatever. Um, that knowledge also helped us develop this test. Radioactive iodine gives off a lot of energy that can be detected from, MRIs or is it MRIs? No, it might be just like scans, right? Um, anyways, I forget which scan it is. That's terrible of me. What you do to have a nice, clean picture of your iodine's health in the hospitals, they'll have the patient drink or they will inject the patient with radioactive iodine and it's giving off lots and lots of energy. But where does all that iodine go? It goes into their necks. So if the iodine is, they drink the iodine, you wait a little bit, and all the iodine will be collected in their throats. And when they take a picture of a person's neck to see what their thyroid is like, this thyroid has this amazingly beautiful glow to it, and you could see it's outlined perfectly well. It's actually pretty cool. Um, so yeah, there's my shameless plug into science. Let's go back to math. The math question says a 100 milligram injection of radioactive iodine is given, 91.7 milligrams is left. So right away, my final is 91.7 milligrams. My initial is 100 milligrams. This is 1 over 2 to the power of, um, if 91.7 milligrams of radioactive iodine is left in the body after 1 day, what is the half-life of the radioactive iodine? Let's do this again. A final is 91.7. A initial is 100. The amount of time that I wait is 1 day. The question is asking what is my half-life? And by half-life, this is a symbol called lambda. It's sort of like a little house roof, okay? A little smaller line, longer line, like that. Plugging into the formula, 91.7 is equal to 100 times 1 over 2 to the power of 1 over lambda. Our goal is to figure out what lambda is, which means I need this exponent to somehow be isolated. You can already guess I'm going to be using logarithms. Let's first divide both sides by 100, leaving me 0.917 equals 1 over 2 to the power of 1 over lambda. Next, I am going to log both sides so that I can drop down the exponent. Log of 0.917 is equal to that log of half. Okay, now I'm going to do some algebra and rearrange it so that 1 over lambda is equal to log 0.917 divided by log of half. I'll write that down. Log of 0.917 divided by log of 0.5, which gives you, so 1 over lambda is equal to 0.125006. And that means lambda is equal to approximately 8. So the half-life of radioactive iodine is 8 days. And there's my question. So here's some simple ways, and again, by summarizing, the solution of these, example 3, was found by, once again, logging both sides. Okay. So again, the substitute can pause the video as they see fit. Example 4 and example 5 are going to dabble into some trinomial or factoring style questions. So let's move on when you are ready. Example 4, as I said, is a factoring example. So take a look. You might notice that there's a, let's rearrange it so that I do have myself a trinomial. Okay, so how it looks somewhat similar to a a trinomial that you can factor, but how do I make this a bit more familiar? Hmm? How might I turn this into a form like this? Because if I had something like that, it would be it would be easy to factor. Should I think about it? Going once, going twice. Yeah, I'm going to substitute. I'm going to ask a to equal 3x, all right? Because, it sort of makes sense. So how do I get 3 2x and change it up to our advantage so that I can substitute it? Well, we're going to use your exponent laws. 3 to the power of 2x can be rewritten as 3x to the power of 2 plus 3x minus 20 equals 0. And how can I say that 3 to the power of 2x is equal to 3 to the power of x to the power of 2? Well, remember our power rules for exponent laws. If 2 to the power of 2 is to the power of 3, you can say those two are being multiplied. And in the same way, 2 to the power of 6 can be rewritten as 2 to the power of, let's switch it up, 3 to the power of 2. When you have a power of a power, it's essentially multiplication. So if I have something that is a multiplication, I could say it came from a power of a power. Now if I substitute, I have myself a squared plus a minus 20 equals a 0. And if I factor, I'm hoping here you feel that you are in familiar territory, so you can solve this. In essence, a equals -5, a equals 4. So those are my two situations. A, or in this case 3x, equals a -5, and 3x equals a 4. Between these two, however, one of them we can actually reject. We can reject this one. Why? Going once, going twice. It is because no value of x will allow me to have a negative answer. This is impossible. No solutions. Therefore, here we are. How do we get x down and how do we figure out the x? Well, you can rewrite this. There are two ways. If you know the nature of an exponent, you know that log of base 3, when the answer is a 4, my exponent is x. You can plug that into the calculator, which is hard. You'll have to do log 10 of 4 divided by log 10 of 3. And you get your answer, which happens to be about 1.262. Another way you can do this is just go ahead and log both sides like before. If I log both sides like before, this is log 3 of x equals log of 4. And by power law, the x can drop down, which is log 3 equals log 4. And if I isolate for x, I get log 4 over log 3, which happens to be exactly like the other way. So you can do whatever method you want, whatever works. You will still get the final answer. Some people might be copying this down. That's fine. If you have copied it down, give the second one a chance. Okay, the solving this root of 2x business is the same situation as above. Knowing that there might be some kind of trick that involves a root 2x, you see that these two, maybe there's a trick involved to turn them into a trinomial. I'm going to ask the substitute to pause the video and give everyone just a minute. You don't have to solve all the way. See if you can use 1 minute to turn this into a or I guess minus a plus minus something equals 0, right? Try to turn that into a trinomial. Right. Assuming that you had a chance to try it, the correct substitution, or the simplest substitution, is literally just changing square root of 2x into a. And just so you know, this is also equal to 2 to the power of x divided by 2. They're the same thing. So the square root is a. This would be 12 over a, and that would be just 1. I don't like the fraction. I'm going to multiply every single term by the a value. This becomes a squared. This becomes negative 12, and that becomes a. If I rearrange it, this becomes a squared minus a equals 12. And once again, you're in familiar territory. A minus 4, a plus 3, which means square root of 2x equals 4, and square root of 2x equals negative 3. Once again, between these two, there is one value that we can completely reject, and that is this one. You might be wondering why, when you have a square root, can't you get a negative value? This is true, but think about it this way. Instead of doing a square root, imagine this was actually written as an exponent. Even if I have a fraction here, does any value of x allow me to have a negative value? The answer is no. And therefore, this is rejected. This is okay though, right? So we have 2 to the power of x over 2 equals a 4. And how about this? Let's use our skills from 2.1. 2 to the power of x over 2 is the same as 2 to the power of 2. That means x over 2 must equal 2. That means x has to equal a 4. Yeah? All right. Once again, I will ask the substitute to pause the video as they see fit and move on to the next example once people are good. At this time, I want to invite everyone, if you do have a question or you have absolutely no idea what's going on, see if you can watch the video again on your own time or reach out to me through email and ask away. The example 5. Example 5 is a little bit funky and you're going to use exponent laws. There's no real way to get around it. Looking at this, yes, there is a trick. We can't create a trinomial, right, that we can factor if we have a negative exponent. So we're going to try to figure out a way to get rid of that exponent. How? Well, I'm going to turn it into a 0. Consider this. Just like before, right here, we multiplied everything by an a value so that we get rid of a denominator. We can actually do the same idea to get rid of a negative exponent. How? Multiply everything by 2x. Oh, sorry, 2 to the power of x. Why the heck am I doing this? Well, consider how the negative exponent gets resolved when I do this. Okay, so 2x, 2 to the power of x times 2 to the power of x. Well, the exponents add, this becomes 2x. 2 to the power of x times negative 2 to the power of negative x. Remember, when you're multiplying exponents of the same base, the exponents, oh sorry, if you're multiplying powers of the same base, the exponents are going to add. So what's x added to a negative x? It's a 0. This one, that's just 4 times 2x. So what happens to the negative x exponent? It disappears. So here, I should do an equal sign. The next line is now 2 to the power of 2x minus 1. I'm going to bring this to the other side. Minus 4 times 2x equals a 0. And if I rearrange it, does it look sort of familiar? I hope so. This is 2x, just x, subtract by 1, equals 0. It's exactly the same situation as before. And if you don't see it, here's a final line. 2 to the power of x is to the power of 2 minus 4, 2 to the power of x minus 1 equals a 0. Yes, you can substitute. This becomes a squared minus 4a minus 1 equals a 0. I'm going to ask you to try to solve this. And hint, this is not factorable. So there's another way you're going to have to work around this. And again, you'll probably find a value where you can't solve it. It has to be rejected, while the other one is okay. Okay, the answer keys are going to be available online, so why not give that one a shot? And that brings us to the end of this lesson. There are plenty of questions that you can try from the textbook. A textbook will be provided to the substitute so that you can take photos of it and bring it back to your table if you don't have it. Otherwise, I really hope that you will have a great holiday. You'll have a great long break. Please also remember, just in the back of your head, that you do have, there is a possibility that something happens after the winter break. It did happen last year, so who knows if it's going to happen this year with Omicron just around the corner. In the second half of the class, after the break, you are going to be subject to some instructions for your portfolio assignment. So stay tuned for that. Okay? Uh, yeah, study hard, and we'll see you after the break.